In this video, I'm going to show you 3 different ways to argue that 2 different logical forms are actually logically equivalent. So what do I mean by this? I'm going to begin with a particular pair of logical forms, not P or Q and not P and not Q. And the question is, are these 2 different things the same or are they going to be different? In fact, they're going to be the same and it's going to be a very important law in logic called DeMorgan's law. But how can I figure that out? Now, the first one I'm going to do is not really much a proof, but it's sort of test of reasonableness. I want to just make up some example, make up a P and make up a Q and see whether you can just sort of reason it through and get a result that makes it look equivalent. So, for example, what if I set to be P is Trevor is a unicorn and Q is Trevor is a goldfish? Something ridiculous. Now, if I think about the left-hand side here, so the not P or Q. So P or Q stands for Trevor is a unicorn or Trevor is a goldfish. And then when you put a not all the way out the front, what you're saying is that it is not the case that Trevor is either a unicorn or a goldfish. That's one way I could come up with an English sentence for that logical expression. Now, for the right-hand one, I'm saying not P and not Q. In other words, I'm saying that I am not a unicorn and I am not a goldfish. Now, it's a silly example, but if you look at these 2 different things, do you think that they are the same, they express the same idea, or a different one? Well, if I look at the left-hand side, if I'm saying it is not the case that I am either a unicorn or a goldfish, it really means I can't be either of those. Which is basically what the right hand is saying as well. It's saying I can't be a unicorn and I can't be a goldfish. So it seems reasonable to me, but maybe you say, well, hold on, that's not actually a proof. I want something more. Now, the way we had defined a logical equivalence was to say, go and look at the truth table. So here is this truth table for the so-called DeMorgan's law. I set my P and Q to be a bunch of different true and falses. I have some intermediate values that I've put here, like the not P and the not Q and the P or Q. And then finally, the final 2 columns are the left-hand side and the right-hand side. And you'll notice that because they match, because it's false, 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 true, that means these 2 different sides are logically equivalent by definition. So this is the more formal proof of the reasonable test that our sort of English sentences gave us. Now, there are an enormous number of these logical equivalences out there. There's a couple that are pretty major, so we can list them off by name. This one that I did, this DeMorgan's law, but there's actually 2 versions of DeMorgan's law where you permute the or and the and statement. But we've seen previously we had a double negative law. We had a truth table showed the negation of P was P. And then when we talked about tautologies and contradictions, there were also a bunch of different laws that applied there. There was these identity laws that said if you took something like P or a contradiction, that's just P. There were these universal bound laws like that P or a tautology was a tautology. And there's many more that I haven't put up on this list. So this brings me to my 3rd way of showing a logical equivalence. You don't always have to go back to a truth table. If you want to, now that you know all of these are logical equivalences, you can cite them in the proof of a new logical equivalence. Let me show you what I mean by this. Let me begin with this messy statement over here. What I'm going to try to do is clean it up, manipulate it into some other logical statement, but where all of my manipulations are the rules that we just saw on the previous slide. That is, I'm not doing a truth table, I'm applying a list of rules. So, when I look at this thing, there's many ways I could start, but the first is I could apply a DeMorgan's in the middle. There's a not, and then there's an or statement of 2 different things. So let me do that. Let me apply my DeMorgan's law. So what happens? The not goes in front of the P, the or flips to an and statement, and then finally, the left-hand side and the right-hand side, there was this not Q. So when you bring the new not in, what you get is not Q. And then finally the and the tautology on the out-hand side. I haven't touched that one at all. Okay, well, now I could do a double negative thing. I have a not Q here, so let me apply my double negative rule, and so this is just not P and Q, and then finally and a tautology. Okay, it's already gotten a little bit cleaner. Well, what about this thing where I've got a big thing in brackets, and then I put and a tautology? Can I clean that up? Well, one of the rules we had before, an identity rule, is if you have any statement, you go and a tautology, that is exactly true and exactly false based on the original statement. The and a tautology part doesn't do anything. So by this identity law, we can just get rid of the and a tautology thing. And so now we've cleaned it up when we say this is logically equivalent to not P and Q. So the point here is that you don't always have to go back to a truth table, which can be somewhat long and cumbersome. If you have this list of known logical equivalences, you can apply them in sequence, citing the name of the logical equivalence as you do, and you're able to take one logical form and manipulate it into a different logical form.